The Heisenberg Uncertainty Principle is one of the most famous results in all of physics. It states that the position and momentum of a particle cannot both be known with arbitrary precision at the same time. In standard quantum mechanics, this is treated as a fundamental law, an irreducible feature of reality with no deeper explanation. Particles simply do not have definite position and momentum simultaneously. That is just how the universe works. Wave physics dissolves this entirely. Not by finding a loophole and not by disputing the experimental record, but by asking what position and momentum actually are. Position is a single measurement. Where is the object right now? One snapshot, one answer. In wave physics, it is the location of a distortion on the membrane, resolved to the nearest unit of measurement. There is nothing ambiguous about it. Momentum is not a single measurement. Momentum is mass times velocity. Velocity is distance divided by time. Distance divided by time requires two position measurements separated by a time interval. Where was the object then, and where is it now? Momentum is not a property you can read off an object at a single instant. It is a relationship between two observations. This is the entire source of the apparent incompatibility. A perfect position measurement is an instantaneous snapshot. It tells you where the object is at one moment and nothing else. A momentum measurement requires two snapshots separated by time, during which the position has changed. The two requirements pull in opposite directions, not because reality is fundamentally indeterminate, but because the two quantities are defined differently. One requires one measurement, the other requires two. And here's the point the uncertainty principle overlooks. At the moment the second measurement is completed, you have both. Position is the location recorded by the second snapshot. Momentum is the displacement between the two snapshots divided by the time between them. Both are known at the same instant. The uncertainty principle claims this is impossible. Wave physics points out it has just been done. This is not a peculiarity of subatomic physics. Consider a musical tone. To establish that a sound has a definite frequency, it must persist for some duration. A tone lasting only an instant contains all frequencies simultaneously and has no definite pitch. You cannot have both a perfectly defined frequency and a perfectly defined moment of occurrence. The uncertainty principle is this same mathematical relationship, expressed in the mechanics of the membrane. The stronger form of the uncertainty principle, developed after Heisenberg's original formulation, goes further. It claims that uncertainty is not merely a consequence of measurement disturbance, but an intrinsic property of quantum states. The evidence cited is ensemble measurements. Position is measured on some targets, momentum on others, and the spread in results obeys a specific inequality. Wave physics identifies a hidden assumption in this argument. Measuring position on one target and a single snapshot result on a different target is not measuring momentum. Momentum requires two measurements of the same target. The ensemble spread reflects the Fourier properties of waves, which wave physics fully acknowledges, but it does not demonstrate that any individual particle lacks definite position and momentum simultaneously. A distortion in wave physics always has a definite position at every tick of the membrane. Its momentum, being a relationship between two positions separated by time, is simply not defined at a single instant. Not because it is uncertain, but because it requires more than one instant to exist. There is a practical limit, and it is real. At the subatomic scale, any available probe carries enough energy to disturb the target materially. If you measure the position of a speeding bullet by hitting it with another bullet, the result will be uncertain. That does not mean the first bullet lacked a definite path. At subatomic scales, every available probe is a demolition derby relative to its target. The practical limit is a limit of instrumentation, not a limit of reality. The uncertainty is in the measurement, not in the target. In the final video, we summarize the challenge that wave physics represents to the standard model of particle physics.